Have you ever wondered what everything is made of? Your desk? Your lunch? You? It's all made of atoms. Atoms are the super tiny building blocks of the universe. You could fit millions on the period at the end of this sentence. Isn't that wild? Everything you can see, touch, even breathe. They are the fundamental pieces of matter, the Legos of reality, each one a tiny world of its own, waiting for us to explore and unlock its secrets. So, what's inside an atom? Let's take a look. In the very center of every atom is something called the nucleus. Think of it like the pit of a peach. It's small, it's dense, and it's packed with energy. The nucleus itself is made of even smaller particles, protons and neutrons. Protons have a positive electrical charge, like the plus sign on a battery. Neutrons have no charge at all. They're neutral. These particles are held together by an incredibly strong force, one of the most powerful in the universe. It's what keeps the atom's core from flying apart. But that's not all. Whizzing around the nucleus are even tinier particles called electrons, like planets orbiting the sun. Electrons have a negative charge, like a battery's minus. The proton's positive pull keeps electrons in orbit. This attraction holds the whole atom together in a stable, balanced system. A beautiful tiny dance, a cosmic ballet in miniature. The number of protons makes each atom unique. Hydrogen has 1, oxygen 8, uranium 92, and it's special. Some heavy atoms are a bit wobbly. That instability can unlock tremendous energy, like a wound spring. And that's where nuclear science gets really exciting. Consider the possibilities. So how do we get energy from these tiny atoms? One way is through a process called nuclear fission. Fission is just a sciencey word for splitting something apart. Here, the nucleus of a heavy, unstable atom like uranium. Scientists shoot a tiny neutron at the uranium core. It's like playing a game of cosmic pool. When the neutron hits just right, the nucleus becomes extremely unstable and splits into two smaller atoms. When it splits, it releases a bunch of energy, mostly heat, and 2 or 3 more neutrons. Now think about what happens next. Those new neutrons strike nearby uranium atoms, causing more splits, more energy, more neutrons. This creates a chain reaction. Each split triggers more splits, releasing a massive amount of energy very quickly. It's this controlled chain reaction we harness in nuclear power plants to generate electricity. Now there's another way to get energy from atoms: nuclear fusion. If fission splits atoms apart, fusion is the opposite. Fusion happens when we take 2 very light atoms, like isotopes of hydrogen, and squish them together. We smash them under incredible heat and pressure, hotter than the center of the sun. When they fuse, they form a slightly heavier atom, like helium, and release mind-boggling energy, the same process that powers the sun and stars. In fact, fusion can release even more energy than fission, and produces very little long-lasting radioactive waste. The challenge is starting and sustaining fusion. It takes tremendous energy. Scientists worldwide are working to crack it. And if we do, it could change our world forever. So, we have this incredible energy from fission. How do we use it to turn on our lights? It's actually pretty simple when you break it down. Inside a nuclear power plant, the fission chain reaction heats water into a huge amount of high-pressure steam. This is similar to coal or natural gas plants. We're just using a different heat source. The goal is steam, lots of it, to spin a giant fan-like turbine. Imagine blowing a pinwheel to make it spin. Same idea, just much bigger. The turbine connects to a generator, magnets and coils of wire. As it spins, it creates a flow of electrons. What do we call a flow of electrons? Electricity. Electricity travels through power lines to our homes, schools, and businesses, powering everything from our refrigerators to our video games. Nuclear science isn't just about electricity. It's a powerful tool in medicine. Doctors use small, safe amounts of radioisotopes to see inside the body, helping diagnose cancer or heart problems without surgery. It's like X-ray vision that can pinpoint problems with amazing accuracy. Radiation therapy uses carefully aimed beams to damage cancer cell DNA and stop them from growing. From powering cities to healing the sick, understanding the atom profoundly benefits humanity. The promise of nuclear energy. When you're dealing with atomic energy, safety is job number 1. Absolutely. Plants use multiple layers of safety. The reactor is inside a massive, super strong containment building. Steel-reinforced concrete, several feet thick, built to withstand earthquakes, airplane impacts, and extreme weather, like a fortress keeping radioactivity locked inside. Inside, control rods are crucial safety features. They soak up neutrons that keep the chain reaction going. If the reaction speeds up, operators lower the rods to slow or stop it, like hitting the brake pedal. Systems are constantly monitored by highly trained operators and automated computers. One big advantage is environmental. Unlike coal, oil, or natural gas, nuclear plants don't emit greenhouse gases like CO2. Cutting greenhouse gases helps protect our climate while delivering reliable 24/7 clean power. Scientists are developing even safer reactors and pushing the boundaries of fusion, the sun's power. Imagine nearly limitless, super clean energy. That's the promise of fusion. Nuclear science can power a growing world, explore space, and advance medicine. Used wisely and safely, the atom builds a brighter, cleaner future for everyone. Science is the key.